section is do 2 videos. One that talks about just the nuts and bolts of what's in the chapter, and in the other one, I'm going to talk about the proofs. So you don't get bogged down with the proofs, as anybody who was in class on Tuesday will tell you that that can be a little bit of a headache. So, equivalent sets and finite sets. The first thing I want to do is remind you of 2 theorems we had before. One of them said that if F is a mapping from A to B, and G is a mapping from B to D, and A and B are disjoint, their intersection is empty, then if I take the union of F and G, I still have a function going from A union B to C union D. Another theorem that's going to come up that we're going to need, though there's more in the proof section than this section, if F is a mapping from A to C that's 1-to-1, and S is any subset of A, then if I take F and restrict it to just the set S, it will still be a 1-to-1 mapping from S and to C. Okay, what is this chapter all about? First we want to talk about what an equivalent set is. 2 sets A and B are equivalent if and only if there is a 1-to-1 onto mapping from one set to the other, from A to B, and we will say that A is squiggly line B. Oddly enough, or not so oddly, equivalent sets, this forms an equivalence relationship. This relation is reflexive, symmetric, and transitive. For example, let's look at these 2 sets. If you have 2 finite sets, and then you can draw lines to show we have, and this is just one, there's several, but here's a 1-to-1 onto mapping from A to B. They both have 3 elements. They are equivalent. Any 2 finite sets with the same number of elements will be equivalent. Let's look at something that's not finite, the interval 0, 1 to the interval 0, 2. If I look at the function f of x equals 2x, this is a 1-to-1 onto mapping from the interval 0, 1 to the interval 0, 2. So in terms of equivalence, we say that this set, interval 0, 1, is the same, where same is equivalent, to the interval 0, 2. This one's fun. Okay, so we have the interval going from 0 to 1 is equivalent to the set interval going from 0 to infinity. Now here's a function, but let's look at a picture. It's easier to see. I don't know if you see that yet. Oops. You should see this. So imagine I have an asymptote at 1. So I can take the interval from 0 to 1, not including 1, and stretch it up so that as I approach 1 from the negative side, I will go up towards infinity. This is an asymptote. And this is just an example of a function that I can use that reacts like this. Another cute equivalency that I like, especially when I do topology, let me make sure you can see this. Okay. A circle is equivalent to a square. So imagine you put the circle inside of a square and you draw a dot somewhere in the circle. To figure out what points in the circle go to what points in the square, draw a line from the circle, from the point in the circle out. So where the line crosses the circle, that point will get mapped to where the line hit, or ray, if you're going to be anal-retentive, where the ray hits the B. It hits the square. So I know this is onto because if I pick any point on the square, all I have to do is draw between this point and the blue point, and I go, oh looky, this point on the circle will get mapped to that point on the square. It's 1-to-1 because, it's 1-to-1 because if I have 2 points going to the same, I can't have two points going to this, 2 different points going to the same point on the square, because that would mean I don't have a straight line, and that doesn't, and I define it to be a straight line. So let's look at some theorems about equivalency. If A, let's get this so you can see it. If A is equivalent to B and C is equivalent to D, well then I can say A cross C is equivalent to B cross D. So this is a way to kind of stitch 2 sets together and keep the equivalency. But what about union? That one's a little bit trickier. If A is equivalent to B and C is equivalent to D, I need the intersection of A and C to be empty and the intersection of B and D to be empty, then their unions will be equal. Because if these guys overlap a couple and these guys don't overlap, then it doesn't make sense to say they have the same number of elements. Consider if they're finite. So we need them to be separate. So, definition. if A is a finite set, and let's say it has an n number of elements, where n is some natural numbers, then we say the cardinality of A is n. Cardinality is going to be our way of talking about size when our size gets into infinities, different sizes of infinities. We will denote this with a couple of lines over the set. So this is saying the cardinality of A is n. The cardinality of the empty set is 0. Definition. So I need this kind of canonical, this basic finite set. Oh, but we don't know the word finite yet. We will in a second. So for any k in the natural numbers, we call n sub k the set going from 1 up to k. So for example, n sub 3 is 1, 2, 3, n sub 2 is 1, 2, n sub 100 is, I'm not going to say all those, that's a long list. We define a set to be finite if and only if it is empty, or it is equivalent to n sub k for some k in the natural numbers. That is our definition of finite, and whenever we prove something is finite, we have to use this definition or go to a theorem that we have proven. Theorem. A is finite and A is equivalent to B. That implies B is finite. So to prove that B is finite, I need to show that it's equivalent to some n sub k. This is going to be pretty straightforward, because if A is finite, it's equivalent to some n sub k. A equivalent to B means there's a one-to-one onto mapping here, so by the transitive property and hubba hubba, then I can get that B is finite. Now, like all things, when we start off, we have to do little picayune kind of lemmas and theorems and things to build up to the big theorems. And this is no different. So this theorem says, basically, if you have a finite set and you add something to it, it's still finite and it's got one more element in it. So if the cardinality of S is k and x is some element not in S, if you take S union x, you will have a set of size k plus 1. Okay. Hopefully that's a duh. Every subset of n sub k is finite. Well, we have to figure out a way of proving that. I need to come up with a generic subset. I can't say, well, consider the set 1, 2, 3. No, I have to come up with a generic subset A or B or Q, whatever your favorite letter is. And then I need to somehow show that that subset is equivalent to some n sub k. Using this theorem, I can then prove that every subset of a finite set is finite. This is much more interesting. We're going to want to use that a lot. What about if you take two finite sets and put them together? Well, we need to build up to that slowly. Well, one theorem is not so. If A and B are finite disjoint sets, then A union B is still finite, and the cardinality of A union B equals the cardinality of A plus the cardinality of B. Okay. If the two sets are not disjoint, then what happens is, consider if this is A and this is B. And let you see what I'm actually writing. If this is A and this is B, the union, if I add the cardinality of A with the cardinality of B, I will double count this section in here. So if the two sets are not disjoint, we'll say that we know that their cardinality, A union B, is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. Since it was double counted, we need to subtract one version of it. Next, we know we can use induction to show that, since we know the union of two finite sets is finite, I'll be able to use induction to show that the union of finitely many finite sets is finite. So if you take the union of finite sets, it will still be finite. Last couple theorems I want to talk about in this section that are good to have. Lemmas not so much as the theorems. I'm trying to get this thing to focus. Focus. Is it focused? I hope. Okay. Lemma. If R is an element of the natural numbers greater than 1, then for every x in n sub r take away x, the cardinality of that is r minus 1. So in other words, if you have a set with r elements in it and you take one element out, then its cardinality is 1 less. This will help us prove the pigeonhole theorem. Pigeonhole theorem is the idea that if you have 40 pigeons and only 30 pigeonholes, some pigeons are going to either be left out in the cold, or they're going to be more than one pigeon in a hole. That's where the name comes from. But same idea, but now talking about it mathy-wise. Suppose we have r and n are natural numbers, where n is greater than r. And I have a function going from n sub n, the bigger one, to the smaller one. Then there ain't no way that function is 1 to 1. You're going to have two pigeons in a hole. It's going to get crammed in. So that's the pigeonhole principle. We can use this to show that if A is finite and A is not equivalent to any of its proper subsets, sorry, wrong emphasis on the syllables. Start it again. If A is finite, then A is not equivalent to any of its proper subsets. Think about it. If you've got a set of size 5 and you want to come up with a 1-to-1 onto mapping to a set of size 4, ain't going to happen. But when we get to infinite sets, we will be able to do this. We will be able to find a 1-to-1 onto mapping from, say, all natural numbers to just the even natural numbers, or just the odd natural numbers. That's going to be how we distinguish between finite and infinite, is that you can pull this weird crap with the proper subsets. So that's the gist of this chapter. I will do another video soon on doing a lot of the proofs for this section. And the next one the next nuts and bolts one will be about infinite Aleph knot size sets. I'm trying to find the turn off button. Where's the turning off button?